So welcome to our second study session on quantitative methods, this one covering some applications. And in this reading we'll cover some common probability distributions that we'll run into in our finance work and introduce a lot of terms and a lot of information. So as usual, let's get started and have some definitions and some new terms to take into account. We've got a probability distribution, gives the probabilities of all possible outcomes for a random variable, and we'll have an example of this. When we talk about a discrete distribution, it's got a finite number of possible outcomes. But when we talk about a continuous distribution, there's really an infinite number of possible outcomes. So we have to treat these a little bit differently. As examples of a discrete random variable, think of the number of days next week on which it will rain. Well, that's a random variable, but it can only take on these 8 values here, either 0 days, 1 day, 2 days, 4 days, whatever. Now, if we talk about the amount of rain that'll fall next week or next month in a given area, that's a continuous random variable. However, it just depends on how finely we can measure it, right? So any 2 values that you give me for inches of rain or centimeters of rain, we can find another one in between them. So that's what we mean that there's an infinite number of possible outcomes. So with a continuous random variable, the probability of any single value we treat as 0 because there's an infinite number of single values. So when we talk about probabilities with a continuous random variable, we'll talk about the probability of the random variable being within a particular interval. Now, a probability function is for a discrete random variable. And here's an example at the bottom of the slide here. We've got the probability of x, and that's one of our values, is x over 15. And the range, the values that this random variable can take on, 1, 2, 3, 4, and 5. So if we look at the probability of 3 here, it's 20%. 3 over 15, 0.2. And 5 over 15, well, that would be 33.3% probability of 5 for this probability function. And it qualifies as a probability function because there are no negative values. We can't have negative probabilities. They have to be between 0 and 1. And if we add up all the probabilities for the 5 outcomes, it comes out to 100%. Because we've got, 1, 2, 3, 4, and 5 add up to 15, so we've got 15/15ths overall, so that's 100%. When we talk about a cumulative distribution function, this gives the probability a random variable will be less than or equal to a given value. So as we're moving across the distribution, we just keep increasing the probability until, as we get as far to the right, the highest positive number that we can get, that cumulative distribution function is going to be 100%. That is, all the outcomes are less than or equal to that extreme positive value. So for this probability function that we had before, if we denote this cumulative distribution function with a capital F, f of 3, so now we're asking, well, what's the probability of 3 or less? So we're going to add up the probabilities for the outcomes 1, 2, and 3. So we've got 1, 2, and 3, so that's 6/15ths or 40%. So that's our cumulative distribution function. And where we'll run into that is when we're using the standard normal tables to estimate the probabilities of given ranges. And we'll have examples of that coming up as well. Let's look at this example here. We've got a percentage return on equity, and we'll call that X for a firm that's defined over the range minus 20% to plus 30%. It has a cumulative distribution function, and we define this as X plus 20 over 50. What is the probability that the ROE will be positive and less than or equal to 15? So what we're doing here, we're going to use this cumulative distribution function to find the probability for this interval. So greater than 0 and less than or equal to 15. Now, since it's a continuous distribution, we don't really have to worry about whether the endpoints are included or not, because remember, for any particular specific value, the probability is 0. So then we'll look over this interval. So first we're going to look at how we might define this. So we're going to say the probability of being between 0 and 15 is the cumulative distribution function for 15 minus the cumulative distribution function for 0. So if I can draw here one of my great pieces of artwork, some normal distribution, and say we have 0 here and we have 15 here. The idea is this cumulative distribution function f of 15 gives us the probability of that or less. So it gives us all the probability to the left of 15. And then when we subtract off the cumulative distribution function for 0, f0, that's the probability of being less than or equal to 0. So that's what we're up to here, is subtracting that off from f of 15, and the difference is going to be the probability in that interval right there. So moving on with the calculations from our CDF, we find out that that probability is 70%. So our probability of less than 0 is 40%. The probability is less than 15 is 70%. So in that interval, we've got 30%. So just what I want you to take away from that is just how you can use this cumulative distribution function to figure out the probability in any particular interval of the distribution. Now let's start with some of our formal distributions. A discrete uniform distribution, well, uniform here means they all have the same outcomes. It's a discrete distribution, so there's a finite number of outcomes. As an example of this, let's say the probability of x equals 0.2 for these 5 values. So that is a distribution function. Each one is equally likely. So we've got 5 outcomes. 1/5 is the probability, or 20% each. So the probability of the value 2 is 20%. Probability of value 3 is 20%. And when we say f of 3, the cumulative distribution function here, that's going to be 3 or less. So that's just 3 out of the 5 outcomes. So that's a 60% probability of getting a 1, 2, or 3. Now we're going to define a binomial random variable. When we run into a problem where there are only 2 outcomes, then we can often use this binomial function depending on what the question is we're being asked. And we usually designate one of these outcomes as success, but that's not really important. We can calculate the right values either way. But we're going to ask a question, well, what's the probability of exactly x successes in n trials? The examples we'll often use is a big urn of black and white balls, and we want to know, well, if you choose 5 balls at random out of there, what's the probability of getting exactly 3 black ones? Not 2, not 1, not 5, but exactly 3. And so that's what we're defining the probability for here, is that exact number of successes. So let's look at an example with some black and white marbles. We've got a bowl. We're going to have 6 tries or 6 draws from the bowl. And we said the probability of selecting white is 0.4, 40%, each time. And these trials are going to be independent. So maybe we put the marble back in the bowl to keep the probabilities right. So if 40% of the balls in there were white and 60% were black, then our probability of success would be 40% for a random draw. Now here, x equals 2, because we're getting 2 successes in 6 tries. The probability of success is this 0.4, and n is the total number of draws. So that's our notation for the formula. And here's the formula. Looks a little daunting, but let me take you through it. I think, as with a lot of these formulas, if you understand where it's coming from and the sense of it, it'll be a lot easier to remember and to apply. So what we've got here is the probability of 2, and that first term, that's that combination formula, n choose x, and then we've got the probability of success to the x, and the probability of failure, 1 minus the probability of success, to the n minus x. And let me just take a second here and clear this slide off a bit and show you exactly what I mean. So we're going to have 6 tries. Well, let's look at one way to get 2 successes in 6 tries. And let's see, success here is a white one, so here's one way to do it. White, white, black, 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 black. Well, these are all independent draws. So the probability of getting a white one is 0.4. That's our probability of success. And we can put 0.4 in there twice. And the probability of failure is 1 minus 0.4. So let's put in 0.6, 0.6, 0.6, and 0.6. So that's the probability of this particular outcome right here. Well, this is 0.4 squared, and this is 0.6 to the 4th power. So that's the probability of getting this sequence right here. Well, what's another way to get 2 white ones in 6 draws? Well, an obvious one would be white, black, white, black, black, black. And we'll see the probabilities are the same, right? Here's our failures. Those are all 0.6. Here we've got 2 successes. Those are 0.4. So our probability of getting that series of draws is exactly the same. So that's where the probability of success to the x, that's our 0.4 to the 2, and probability of failure, our 0.6 to the 4th, come from. Well, that other term, n choose r or n choose x, that is how many ways can I get 2 successes in 6 trials. So what we're doing is taking the probability of one of these outcomes, and no matter how we order them, the probability of that six-ball series is the same, and multiplying it times the number of different ways that we can get 2 successes in 6 trials. So here's the 0.6 to the 4th, here's the 0.4 squared, and this, there are 15 ways to choose 2 white ones in 6 trials. So that's where that formula comes from. Now let's take a look at a binomial tree, and I'll show you how these probabilities turn up. With a binomial tree, I think it's important to understand what's kind of the minimum information you need to construct one. Well, we've got a probability of an up move. We can call that success, but we don't really in this. We just say up move and down move. So the probability of the up move, if we have that, we can figure out the probability of a down move because they have to equal 1. So it's 1 minus the probability of an up move. So we need that probability of an up move. And we also need this up factor. It's a multiplier greater than 1. So let's say that's like 1.12, that the value is going to go up 12%. Multiply it by 1.12. And if we know that, we know the down factor because the down factor just says, well, don't multiply by the up factor, divide by it. And one of the reasons we set it up like that is so if there is an up move, we multiply by the up factor. If there's then a down move, we multiply by the down factor or divide by the up factor. So the point is it gets us right back to where we started. So the other thing we need to construct this tree is a beginning price. So if we have these 3 things, we can construct this binomial tree. So let's continue with our example here. Probability of an up move is 60%. That makes the probability of a down move 40%. Our up factor is 1.12, and the down factor is to divide by that. So here's our tree. We need to know this, we need to know this, and we need to know this, and we can construct this whole tree because there's only 4 possible outcomes: up, 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 down, up, and down, down. So let's look at that top line first. We've got a 60% chance of an up move, and that gives us this value when we multiply by the up factor, 2240. If in the next period, and we've got a 2-period model here, here's the end of our first period. In that second period, if it goes up again, We multiply by the up factor and get a price of 2509. And the probability of getting 2 up moves, well, these are independent trials, so it's just 0.6 times 0.6, so 36%. Probability of 2 down moves, same way, 40% times 40%, so the probability here, 16%. Now these ones in the middle, if we have an up move and a down move, we get right back to our beginning asset price of 20, and the probability of an up and then a down move is 24%, and the probability of a down move and then an up move is also 24%, so there's really 2 ways to get here, so that's why we have this probability of 48%. Over here. So these are our binomial probabilities. That's the probability of, if we define an up move as success, that's the probability of 2 successes, 2 up moves in a row. That's our 36%. So how many? We've got a probability of an up and down move is 24, but remember we've got to multiply it by how many ways are there to get 1 success in 2 trials. Well, there's 2 ways. That's our n choose r. We multiply that times the 24%, and we get 48% as our binomial probability. Right there. And that's what you're responsible for, according to the learning outcome statement, is drawing a 2-period binomial tree for an asset price. Now we're going to introduce the concept of tracking error. It's the total return on a portfolio minus the total return on a benchmark portfolio. Or index. So the idea is if we've got a portfolio and we've designed it to track an index, this tracking error measures how well we are doing that. How far are we from the return on the benchmark that we're trying to match? So as an example, consider a U.S. stock portfolio that has a total return of 4%. If the benchmark portfolio, the S&P 500 total return index or portfolio, is 7%, then the tracking error is simply -3. We've underperformed the benchmark by 3%. And I'm not sure why that comes up in this order here, but it is a term that we will use. So tuck it away and we'll be back to it at some point. Now let's talk about a continuous uniform. We discussed the discrete uniform distribution where every item had the same probability. Here the probability is distributed evenly over an interval. And as an example, we're going to consider a random variable that's continuous uniform in its distribution over the interval 2 to 10. Now one way to think of this, I'll go back to some of my great artwork for you here. How wide is this range here that we've got? Well, we go from 2 to 10. So I'm going to claim, I'll complain later, I'm going to claim that this is 8 wide. Well, we need 100%, right, in the total probability here. So one way to think of it, if we put probability on this axis here, is if this is 8 wide, it must be 1/8 high, which is our decimal 0.0125. And so now, remember what I said before about a continuous distribution. We're going to talk about probabilities over an interval. So here we're talking about the interval from 3 to 5, and we could just shade that in. So it's too wide. Well, the whole range gives us 100% in terms of probability. So we've really got a quarter of that range. And we'll see that what we do is just say, well, it's 2 out of a total of 8, so that's a quarter of this uniform distribution, so that's 25%. So if you think about it that way, and not all that challenging to figure out what's going on with a continuous uniform distribution. So it's not each item, each specific value. That has a uniform distribution. It's that over the whole range, any width, anywhere along there, as long as it's the same width, has the same probability. Okay, next distribution is our big one, our favorite, the one we've all heard of and run into. Before, the bell curve or normal distribution. And we say that the normal distribution is completely described by its mean and variance. And one reason, if you remember when we talked about kurtosis and skew, those are measures that we hold constant. They're the same for every normal distribution. So what changes, what we mean by describing this, the mean tells us where the normal distribution is situated and the variance, how spread out the observations are. So it can be a normal distribution, and if it's dispersion, which we're going to measure by variance or standard deviation, it can be wide. or it can be narrower, more clustered around the mean. And the mean can be relocated. But beyond that, the normal distribution has a given shape, and it is symmetric. So we can talk about probabilities on a normal distribution and make some probabilistic statements, which is what we'll do. For a lot of the rest of this study session. So its skewness is 0, it's symmetric around the mean. Kurtosis, our measure of peakedness and the thickness of the tails, okay, is 3. So we're holding those two constant and allowing the mean and the dispersion to adjust for the distribution. You're also supposed to know that a linear combination of normally distributed random variables is also normally distributed. I'm not sure where that comes up and its importance in what we're learning, but it is in there. You're responsible for it. So we'll say, well, if we have two random variables and we add them together, that's a linear combination. the resulting variable is still normally distributed. Now, with a normal distribution, we say the tails go on forever. So being very far from the mean, there's always a positive probability. It could be really, really, really small. These tails are getting what we say is asymptotically close. To zero, the zero probability line, but they never quite reach it for the theoretical normal distribution. We can also define a multivariate normal distribution, and this is a distribution that spits out, well, if it's a bivariate normal, it spits out two variables. And each of these is normal, and we can also specify, besides the means and the variances of each of these variables, the correlation coefficient or covariance, that is the relation between them. So if we specify that, we can generate a couple of normal and multivariate, well, we could generate several of them as well. So, with a normal distribution, and one of the reasons we're going to find it so useful is that we can define the probabilities within certain ranges. Now here we've got plus 1 standard deviation and minus 1 standard deviation. We're going to say 68% of the outcomes are in that range. Within the range plus or minus, the mean plus or minus 1 standard deviation. And you should remember that number. That's something that you should memorize, as well as this other one. We say approximately 95%. Of the observations are within 2 standard deviations either side of the mean. So the reason we're measuring this in standard deviations, right, we said the standard deviation could change if there's a greater dispersion. But we can't talk about numerical probabilities for numerical values because different normal distributions may be more spread out or less spread out. But when we reduce it down to measuring it in units of standard deviation, then we can rely on these relationships to hold. So here's the ones I want you to remember. A 90% confidence interval, plus or minus 1.65 standard deviations. We said approximately 2 on the last slide, but for a 95% confidence interval, we'll go 1.96 standard deviations either side of the mean. And for 99% confidence interval, 2.58 standard deviations either side of the mean. So let's take a look at an example of how we would use this. The mean annual return is normally distributed on a portfolio over many years with a mean of 11%. The standard deviation of returns is 8%. Calculate a 95% confidence interval on next year's return. So the mean, we're going to center this on 11, and a standard deviation is 8. So once we know that, it's not hard to come up with a 95% confidence interval. We just take the mean plus or minus 1.95 96 standard deviations either side of the mean, and that's our range. And we'll say, well, for this distribution as we've defined it, there's a 95% probability that the next observation of this random variable will be between minus 4.7 and 26.7%. Now the standard normal distribution is how we measure things in standard deviations. We've got what we call a z statistic down here, and we center it on 0. So we take the observation here and subtract off the mean, and so the differences from the mean, well, they add up to 0. So we've adjusted this, so we've taken whatever distribution we have and centered it on 0. And now we're going to take the standard deviation and divide that by that. So our standard deviation of the standard normal distribution is 1, because we're in units of standard deviation. So with this z statistic, we're really saying how many standard deviations away from 0 is our observation x. So that's our transformation here. So that's an important point. The standard normal, mean is 0, we've centered it to 0, and standard deviation, well, we've divided the distances by the standard deviation of this distribution, and so that makes the standard deviation 1, and our results are in units. How many standard deviations from the mean, and that's what's going to allow us to make these probabilistic statements about outcomes and ranges and confidence intervals and all the rest. So let's calculate a probability using the standard normal distribution. For this example, the earnings per share for a large group of firms are normally distributed. We've got a mean of $4 and standard deviation of $1.50. Find the probability that a randomly selected firm's earnings are less than $3.70. Well, how far are we from the mean? We're minus 30 cents from the mean. And how many standard deviations is that? Well, minus 0.3 divided by 150, our standard deviation, we are minus 0.2 standard deviations from the mean. So what we need to find out here, our question is less than $3.70. So we need to know from our probability distribution, here's the mean, here's where we are at 370, and I've got a little better picture of this coming up. But we're trying to find this probability distribution, or this probability from the distribution. And so what we're going to look at is we're going to look at the standard normal table and find out the cumulative distribution function. Remember, that says the probability of this number or less, and look up minus 2 on the table, and that way we'll be able to estimate this probability. So there's our z statistic. That's all I was doing when I said, well, we're 30 cents below the mean, and that is 1/5 or 20% of a standard deviation. So our z statistic gives us standard deviations from the mean, and here that's minus 0.2. So now our problem is to figure out what's the probability of being more than 0.2 standard deviations below the mean. Well, here's an excerpt from the table. This is actually the table for positive z-values. Now, you could be given a negative z-value table, and I'll explain that in just a second, but let's look at what we can do this positive one because it is a symmetric distribution. That's what we're going to rely on. So if we look along the margins, we want minus 0.20, or in this case we're looking up to positive 0.20. So we use the 0.2 here, and we use this column here because we don't want to add anything. This would be for 0.21 over here if we went to this one right here. So that would be 0.21. This is 0.20 that we've identified here. And we get 57.93%. Now, for the negative value, we take 1 minus the positive value. See, we're a little bit to the right in the positive area, and so we've got over 50% in the left-hand tail. But since it's symmetric, the probability of being more than 0.2 standard deviations above the mean is exactly the same as the probability of being more than 0.2 standard deviations below the mean. So we're using that symmetry. Now, if you had a negative z-table, and it would say for z less than 0, that's how it would be identified if you were given an excerpt of that on the examination. In that case, the number here would be this. So every cell on the negative z-table for negative values is 1 minus the value for that same cell on the positive z-table. So we can use that in answering questions and solving problems. So here's a picture of what we did here. We looked up on the table this value right here and found out that this was whatever that was, 57.93 or something, whatever 1 minus this is. Okay. So when I'm talking about the symmetry, okay, we looked up this on the positive z-table and found out that there's 42.07 because we read the 57.93 or whatever it was going that way, 1 minus that. And what is here that we've solved for doing that is also this tail, more than 0.2 standard deviations less than the mean. So we've used that symmetry. So you don't really need a negative z-table. You may be given one. I think there's one given in the back of the curriculum text. I know we have one in the Swayzer notes as well. But on the exam, you may be given the positive values and be expected to know that because of symmetry, you can use those values to solve a problem like this. So we figured out that given this normal distribution, the probability of earnings per share being less than $3.70 for a randomly chosen firm, 42.07%, assuming that those earnings per share are distributed normally as we described them. Some more terminology along the same lines, though. Shortfall risk is the probability that a portfolio return or value will be below a target return or value. So we may have a portfolio and ask the question, well, our target is 5% return. What is the probability that we won't make that? So that's an example of shortfall risk, the probability that a portfolio return or value is less than 5%. And we'll use the mean and the standard deviation of portfolio returns to establish that probability, much as we did with that last example using earnings per share instead of rate of return. Now, Roy's safety first ratio really gives you the number of standard deviations that your target return is below your expected return, or the mean of the returns distribution. And the reason we call it safety first is if we have different portfolios and choose the one with the greatest safety first ratio, we're going to get the one with the least probability of returns less than the target return, or sometimes we call it the threshold return. If you remember back to the Sharpe ratio gave us excess returns per unit of standard deviation. And so that was the excess of the risk-free rate. So if you look at this safety first ratio here, if we put risk-free rate here, then that would be exactly the same as the Sharpe ratio. So sometimes it helps to tie these concepts together. So now we've kind of generalized the Sharpe ratio and said, well, instead of the risk-free rate, we're going to establish our own target return that's maybe based on the client's needs and circumstances, and say, well, the client really needs to hit this value to fund their pension expense, their retirement expense that they have to pay, whatever it is, so they have this target return. And that way you can use this safety first ratio to look at it and say, well, we want to structure this portfolio in such a way as to minimize the probability of failing to meet that target return. So that's what we're up to with Roy's safety first ratio. And here I just wanted to tie those concepts together for you and explain that the portfolio with the largest safety first ratio is the one that has the smallest probability of generating a return, or we could do it in value, dollar value, euro value, whatever, but minimizes that probability of failing to meet that value target or that return target. So we've got two portfolios in our example here, and what makes it difficult to choose, or at least not super easy to choose, is that the one with the higher expected returns also has more risk. And we think investors don't like risk, but they do like higher expected returns. So that's why. If we have a portfolio that has higher expected returns and lower risk than another portfolio, we would say that portfolio dominates the other one, and we wouldn't really have to consider any of our metrics in order to compare them. And when I say those metrics, think back to the coefficient of variation, which we use to compare portfolios as well. So once we've done this, we look at those two portfolios, we calculate the safety first ratio with a threshold or target return of 5%, so we get the excess over the target of the mean, and then we put that in units of standard deviation. So what this safety first ratio is really telling you for portfolio A, it's saying, well, your target return is 0.83 standard deviations below the mean. So now we really want to find out, well, what is the probability of being more than 0.5 standard deviations below the mean? So if we looked up minus 0.83 on that standard normal z-table, we would get a probability of 20.33%. 20% probability that the return on portfolio A will be less than 5%, less than our target return. Portfolio B has a lower safety first ratio of 0.5, so that says our target return of 5% is 0.5 or 0.52 standard deviations below the mean. What is the probability of getting one lower than that? And that's our shortfall risk, is that probability. So here we'd look up minus 0.52 on the negative z-table, and we'd find out that there's a 30% chance of returns lower than that if we invest in portfolio B. So that's how we would use those and how those are related. Our next distribution is a log normal distribution, and probably the easiest way to remember it and think about it is that if we have a random variable x that's normally distributed, this function, that mathematical e to the x, is distributed log normally, or has a log normal distribution. And the reason we like to use this in finance for some applications is it's always positive. If we talk about a normal distribution, it really goes from positive to negative infinity. Well, we can't really model that because prices typically can go to 0 but no lower. So we can model prices, or price relatives, we call it sometimes. It's 1 plus the return. So if we had a value of 0.90, okay, we've modeled this as a price relative, then that's a return of minus 10%. and a minus 100% gets us to 0. So log normal, we use it for prices. It's bounded by 0, and it's constructed by taking a normal random variable, normally distributed random variable x, and transforming all those x's into e to the x, and that's how you get a picture like that. And that's really all you're responsible for here, is knowing that and knowing why we want to use a log normal rather than a normal distribution for some applications in finance. Okay, continuous compounding. Think back to the beginning of our study of quantitative methods, and one of the first things we did is had a stated rate and said, okay, if it's annual compounding, the effective rate and the stated rate are the same thing, stated annual rate. If we do semi-annual compounding, we found out our effective rate is a little higher than the stated rate. Then we did quarterly. It was a little higher still. Then monthly, a little higher still. We could take that further and do daily. We could do hourly. Well, the limit of all of this, when those intervals are infinitely short and the number of compounding periods approaches infinitely many, that's the limit of this, and that's what we have as continuous compounding. So continuous compounding for any given stated rate is going to generate the highest effective return. Now, we usually don't see continuous compounding in our bond products or loan products or securities, things like that, but where it will come up, and it'll come up at level 2 when we start talking about derivatives and valuing derivatives, because a lot of the derivative stuff is done in continuous time. And so we need a continuous rate of continuously compounded rate of return in those formulations. So let's just get some of the basics down that are required for the level 1 curriculum here. Okay? You should know that the effective annual yield with continuous compounding is e to the I minus 1, where I is that stated annual rate. So if the stated annual rate is 8%, we'd put 8 there. But in our example, we're given an effective return. That's not a stated return, stated annual rate. It's a 1-year holding period return of 8%. So that's an effective return. And if we want to find the continuously compounded rate of return, well, let's see. We want the effective annual yield. That's what we've got. So we've got this equals 8%. So we could solve for I there, and that's exactly what we're going to do. But one thing you might need to know is that the natural logarithm of e to the I equals I. So that e function to the power and the logarithm, natural logarithm, says what power do I have to raise e to get this number? So those are just inverse of each other, going back and forth. So we can use that fact. We've got an effective annual yield of 8%. So we can take the log of 1 plus 8%, 1.08, and get 7.7%. So if the stated rate were 7.7%, then the effective annual yield would be e to the 0.077 minus 1. And that's how we would get back our 8%. So see if you can get comfortable going back and forth between a stated rate, stated annual rate, and an effective annual yield using this log function and this e function. And if you remember that the stated annual rate is going to be lower than the effective rate, and you go back and forth, you'll know which is which, and probably be able to answer any problems that come up, any questions that come up, using this formulation. So now, if the ending value is 108 and the beginning value is 100, so that's an 8% effective return over the period, we take the log of that and get 7.7%. And we can go back the other way, as I showed. The effective annual yield with a stated rate of 0.077, 7.7%, minus 1 is 8%, and we get back to our effective annual yield. So let's do another example here. If the continuously compounded stated rate is 8%, what is the effective holding period return for 1.5 years. The reason I wanted to put this in is one of the properties of this is when we have that interest rate in the exponent, we can just multiply that times the number of periods. So what we'll see here is we've got 12, that's 0.08 times 1.5, 1.5 years. Because it's in an exponent, the compounding is all taken care of in that term right there. So that says e to the 0.012 minus 1 gives us the effective holding period return of 12.75% over 1.5 years. And if we're asked how much will $1,200 grow to in 1.5 years at this rate, we can just multiply it. We don't have to subtract the 1 to get 12.75. If we don't subtract that 1, we'd get 1.1275, and that's our multiplier. So here, we just put that term in straight like that. That's our e to the 0.12, 12% over 1.5 years. So then we can just use that as a multiplier, and that's how you'll see it used sometimes, and that's why they've given you this introduction to it in the Level 1 material. Monte Carlo simulation. Whenever you see that term, Monte Carlo, it means we're taking observations from a random number generator, which any computer and a lot of calculators can do these days. So let me set up the use of it. It'll help you understand it better. Let's say we've got a derivative, an option that we're trying to value, and we can't do it with a closed form of formula. And so what does this option depend on? Well, it may depend on interest rates. It certainly would depend on the underlying asset price. It may depend on other factors from the economy, other variables. And so with Monte Carlo simulation, we have to tell the computer the distribution of each of these variables. Its volatility, its standard deviation, its skewness, and what kind of distribution. It may come from a normal distribution, it may come from a F distribution, it may come from any distribution, and then we specify the parameters of the distribution. Clearly, if we mess up this part, we're not going to get very sensible answers, but have some faith that we can do this. And then we'll talk about what we can do if we can't do that. So we specify a distribution for each of these variables, and they say, okay, give us a draw. Give us a random draw from each of these distributions. We could even specify the covariance, the correlations between them. And then it starts to generate these. Well, we generate one set of variables, and then we use those to value the derivative. And we note that value. And then we do it thousands of times. The computer does it thousands of times. Grabs random values for the variables that are affecting the value of the option and calculates the value of the option. So now we've got a whole distribution of thousands of outcomes that show the distributions of the option value based on these random draws of the variables of interest thousands of times. Once we have that, we can look at the mean and say, well, the expected value of this derivative is this. The dispersion, the standard deviation of the values over the whole distribution of possible values based on our assumptions about the distribution characteristics of the underlying variables, and now we've estimated the value and the standard deviation of the value of this option. And so that's one application. We could also do that trying to figure out if a new investment in a project was going to be profitable. We could put in, oh, here's the variable, here's the price of the product, here's the cost of our resources, here's the demand for our product, and how that could possibly change over time. Plug all those in and get thousands of outcomes for the value of the project, and then look at it and say, well, the expected value is this, standard deviation of this. Go back to what we were doing and say, well, the probability of losing money on this project is this tail over here. So that's the way we can use Monte Carlo simulation. But one of the problems is specifying those distributions. Now, in something called historical simulation, we don't have to specify those distributions. We're going to go back in time and look at historical data and select random values of the variables of interest from their historical values. So in this case, we don't have to estimate the distribution of risk factors, but the disadvantage is the future outcomes for these risk factors may be outside the historical range. Well, this often happens when we have a so-called financial crisis, and during the mortgage meltdown or the subprime mess or whatever you want to call it, back in 2007, 2008, you look at that situation and say, well, if we used historical numbers for default risk factors for mortgage securities, we wouldn't have had a clue, and in fact, that's what many houses did, and rating agencies and things like that. They didn't really consider the extreme values that hadn't come about in the past, but surely came about in the aftermath of the mortgage crisis. So that wraps up this reading, and we'll get on to some more exciting probability theory in the next segment.